Cybernetics and Systems. Why talk about systems? We are surrounded by all types of systems. To talk of things is not a rich enough concept. Systems include not only things that have parts, but can also be processes, methods, solutions, or a network. System is a very generic word, and an easy way to say that something acts as a unit or organized whole or has boundaries. Systems are classified as open or closed, physical or abstract, natural or man-made, static or dynamic, deterministic or probabilistic, and so on. We also have social systems, medical systems, political systems, and legal systems, and economic systems. Any arrangement or pattern can be called a system. Systems and cybernetics were born at about the same time in parallel efforts. Both approaches have included the other. Von Bertalanffy, Akoff, and Churchman are exponents on the systems side, and Ashby, Beer, and von Forster are exponents of the other. Systems theory has an engineering approach, whereas cybernetics has focused on how systems function, how they communicate with other systems or with their counterparts, and not least how control is established. Let us say that both approaches are complementary, but even though systems and cybernetics can be viewed as two facets of a single approach, thanks to second-order cybernetics or the cybernetics of observing systems, cybernetics has evolved into a new paradigm for obtaining knowledge. See the cybernetic paradigm below. Who is the observer? The role of the observer is therefore of enormous importance in the reliability of the knowledge obtained. Traditional science has objectivity as its main concern. In cybernetics and systems, the observer is introducing and recognizing a subjective component in his model of the system he is describing from the very start. Because cybernetics deals with models of complex systems, models are not true or false, but rather useful or not useful. In the final run, both traditional science and cybernetics have to recognize that all knowledge can be questioned when a better solution comes along. Under the usual focus, a system is a set of interrelated parts that work together as part of a mechanism or a network. It's also a set of principles, rules, or procedures that describe how something is done. Under the cybernetic focus, a system is something that emerges from a set of interrelated parts. Under Ashby, a system is an observer-dependent list of variables that map into a single valued transformation. I know this sounds a little bit difficult, but what it means is that anything can be a system as long as you can identify how its behavior is repeatable. A related concept, then, is emergence. What makes a system something different from the sum of its parts? What is the difference between linear and circular causality? A linear cause-effect relationship is when A causes B. The effect is produced directly, and B has no effect on A. B can then cause C, and so on, like a chain of events. Circular causality is when a causal link appears that connects A to B, and B can influence A, or even a larger chain in time or space, where it returns back to A somewhat like a bicycle chain. Cybernetics was defined by Norbert Wiener in 1948 as communications and control in the animal and the machine. ASBHY'S definition in 1957 covers almost everything under the sun when it says that cybernetics deals with all forms of behavior insofar as they are regular or determinate or reproducible. Different sciences have derived from cybernetics. For instance, artificial intelligence, information theory, communication theory, chaos theory, computer science, management cybernetics, among many others. It is important to remember that cybernetics was born during the first Macy conferences, where scientists from many different disciplines got together to examine the fact that feedback was a common phenomena associated with those disciplines. In 1990, Stafford Beer gave a conference in Monterrey, Mexico, titled The Intelligent Organization, where he spoke about how the viable system model was used to set up the CyberSyn project for President Allende's government in Chile back in the years 1971 to 1973. Most importantly, Professor Beer explained how traditional science and cybernetic thinking differ in their methods and overall approach. He contrasted the reductionist paradigm against the cybernetic paradigm. These are two ways of looking at the world and could not be farther apart, but both provide us with usable knowledge. Let's look at the list of comparisons. In matters of the structure of knowledge, you have non-contradiction principle against the Ouroboros closure and Gödel's theorem. In matters of logic, you have the syllogism against Hegel and the axiom of internal relations. About describing God, you have theology against Vedantic philosophy. In connection to the cosmos, you have religion, and you have in contrast Zen, where the thing and not the thing are at the same time. In matters of the observer, reductionism has a detached observer, while in cybernetic paradigm you have an involved observer. In matters of science, you have traditional Newtonian science against the science of chaos and catastrophe theory. As in a world vision, you have a billiard ball static universe against an expanding Big Bang complex universe. In matter of method, you have experimentation versus model creation. As far as change is concerned, you have cause and effect versus circular causality. In social control, you have traditional government and management against cybernetics, autonomy, and real time control. And then it goes into, for instance, economic assumptions, where you get an exploitable planet versus Gaia, the living planet. Why do we need models? A model is a representation of a system that preserves the features of interest to the observer. We need models in order to cut down on the complexity of a system we want to study. The key to modeling systems is to preserve the attributes considered important in an effort to replicate them consistently. A model of car can be its shape, or its mass, or its resistance to impact, or something else, depending on what we are studying. We have to remember that in matters of systems, the observer is king. What is complexity? In cybernetics, complexity is called variety. It is the number of different states of a system. Cybernetic complexity leads directly to information theory. The Santa Fe Institute, however, took a different approach to complexity. Listen to Murray Hellman, one of the founders, explain complexity.
Complexity. By what people usually mean by complexity in an ordinary conversation or in most scientific discourse is what I call effective complexity, which in simple lay terms would be the length of a very compact description of the regularities of the entity under consideration. Not the length of a description of the whole entity, but of its regularities. That's effective complexity. You can then make it more technical by introducing the concept of algorithmic information content, the length of the shortest program that would cause a standard universal computer to print out a bit-coded description of the entity and then halt and stop computing.
What is feedback? Feedback is information about the output of a system that returns to change the input. Positive feedback accelerates the output. Negative feedback is error-correcting feedback or information that controls the output. In everyday language, people use positive and negative feedback as synonymous of getting a good comment or a bad comment about something. Most purposeful systems have both types of feedback. One drives the system, and the negative feedback controls it. What is a black box? Black in this case means not transparent. A black box is a system whose internal components or structure cannot be known. The structure is deduced from the way the outputs are related to the inputs. For example, a pigeon is considered a black box. Then, its behavior is predicted by studying how inputs translate to outputs, how rewards translate into behaviors. Another example, you treat the motor of your car as a black box. You do not know how it works, but you know that if you give it enough gasoline, it can power your car. Another example, computers are used to model complex black box systems, manipulating inputs and observing outputs to figure out the original system. How is information related to entropy? The universe is made of energy, matter, and information taken in its most general sense as something that informs or gives form to matter. Information is also a measure of order, while entropy is a measure of disorder. Information has been called negative entropy because the entropy formula was discovered first, and they both use the same formula except that information is entropy with a negative sign. Information is something that eliminates uncertainty. The basic unit of information is a bit, meaning a binary digit. One bit is necessary to carry a message informing about an event that has the same probability of happening as its counterpart. What is a simple system? Simple systems are those that are also obvious. They are transparent in the sense that it is easy to figure out their use. A simple system is a direct cause-effect system, very mechanical. Neither the whole nor the parts have choices. For instance, a hammer, an inclined plane. Many toys are simple systems. In the Cynefin framework, simple systems occupy the bottom right part of the framework. What is a complicated system? A system that is not simple or obvious, but that can be described in full detail. It has many parts, rules, components, whatever. Maybe you need an expert to deal with it successfully. It is a system that is not treated as a black box or does not demand a model to understand it. Some software programs have become so complicated that no one person knows everything there is to know about it. That is a complicated system. For instance, a gasoline engine, an engineering project, such as putting a man on the moon, a Six Sigma management course, all those are complicated systems. What is a complex system? Well, any system whose parts and interconnections cannot be described in detail. Its behavior is, in principle, unpredictable. It's a system that you need a model to describe it. For instance, the human body has too many parts, too many relationships among the parts, and the behavior is unpredictable. Another example, a large business corporation, too many people working, too many clients, too many connections. What is a complex adaptive system? It's a system composed of one or more populations of autonomous agents, all of which are changing their tools or behavior rules to reach individual goals. The agents evolve, the populations evolve, and the system evolves towards some goal. What is management cybernetics? It is a science of effective organization created by Stafford Beer. It makes a practical use of Ashby's law of requisite variety through the organization structure known as the viable system model. This model is also based on the structure of the human nervous system and on the experience of Stafford Beer as an international business and government consultant. What is the purpose of a system? According to Stafford Beer, the purpose of a system is what the system does. The purpose of a system is not what the people creating the system intended. Complex systems frequently acquire their own purposes regardless of intentions. Now, this way of looking at purpose helps prevent complex systems from producing undesirable outcomes. For instance, a hospital may begin producing stubborn infections. A road may produce accidents that other roads do not. According to this definition, think about the universe. What has it produced? Is it a complex system? Does it have a purpose? What is the law of requisite variety? It's also called Ashby's Law, in honor of his discoverer. It says, only variety absorbs variety, which means that the variety of the regulator must match the variety of the system which is to be regulated. In other words, the control variety must match the perturbation variety. For instance, a parent must anticipate every possible behavior of his child in order to make sure the child does not get in trouble. In the picture, an extreme example of control variety. For instance, another example, the desired room temperature has to be matched by the setting of the thermostat and its ability to activate the heater. We can say that our bodies have requisite variety in controlling our body temperature, unless we're sick. Here is a more technical application of the law of requisite variety, as it is used to describe the inevitable variety strategy in a corporation or government. It shows the need to balance the management's variety with the operations variety, and then the operation with the environment. What is the UMS7 model? Stafford Beer posed two questions. What is the uniform basic commodity that we have to deal with in managing and organizing? Is there one thing underlying the problems of men, materials, machinery, and money? The answer is complexity. Well, the VSM as well as the UMS7 model use that insight to model the information flows between the systemic functions of a corporation. If you do not get this right, the corporation will malfunction. The systemic functions of the UMS7 are precisely 7. They are shown here. They should help guide you in setting up the underlying structure of your business. If you look closely, here are the 18 different control loops that have to operate as channels between the different functions. Thank you.